Welcome back to The Explainer. Today, we're doing something really cool. We are going to unlock the fundamental physics of how things move. And honestly, by the time we wrap up, you will literally be able to predict the future. Well, the future of motion anyway. Think about it. Absolutely everything in our universe is moving. Even right now, sitting perfectly still, you are on a giant rock hurtling through space, right? But to wrap our heads around that grand cosmic scale of movement, we've got to start with the absolute basics. We're going to strip away all the messy real-world complexities and just look at the pure, undeniable rules of how an object gets from point A to point B. So here is the game plan for today. We'll kick things off by defining linear motion, then pit speed against velocity, and check out the true power of acceleration. After that, we'll dive into kinematic formulas, see how gravity creates freefall, and wrap it all up by visualizing everything with some graphs. Let's get into it. Section 1. Defining linear motion. Moving in a straight line. We really have to set our baseline first by looking at literally the simplest form of travel there is. And that simplest form is, you guessed it, linear motion. In the physics world, this is strictly defined as the motion of an object in a perfectly straight line where its direction does not change. Period. Picture a sprinter absolutely tearing down a 100-meter dash in a perfectly straight lane, or, just standing on an escalator steadily gliding up to the next floor. This is fundamentally different from non-linear motion, like think of a spinning top or the Earth orbiting the sun. Those involve continuous, constant changes in direction. But for our baseline today, we're keeping things strictly, beautifully straight. I mean, just take a look at this. It brilliantly captures the whole core concept. Going directly from point A to point B without ever curving or wandering off path. No detours, no unexpected turns, just pure, unadulterated linear progression. But to truly measure this kind of journey, we've got to understand the difference between just moving and moving with a specific purpose. Which brings us to section 2, speed versus velocity, the power of direction. This is where we add our very first layer of complexity and discover that in physics, direction is pretty much everything. In our everyday conversations, we tend to throw the words speed and velocity around like they mean exactly the same thing. But in physics, they are entirely different beasts. See, speed is what we call a scalar quantity. It only cares about magnitude, which is really just a fancy scientific word for how much or how fast. It basically just asks, how much ground did this object cover in a given time? Velocity, on the flip side, is a vector quantity. And vectors, they care about two things, magnitude and direction. Velocity isn't just about how fast you're going, it's about how fast you're going and exactly where you are headed. If you're running 5 meters per second, hey, that's your speed. But if you run 5 meters per second straight north, now you're talking velocity. It's a massive distinction. Actually, let's look at this car on a circular track. It's the perfect way to test this exact difference. Let's say the driver has the cruise control set, so the speedometer reads a perfectly steady 40 kilometers per hour the entire time. It has a constant speed, right? But because the car is traveling in a circle, its direction is constantly changing every single millisecond. And here is the kicker. Because its direction is changing, its velocity is constantly changing. It's kind of wild to think about. You can have a rock-steady speed, but if you nudge that steering wheel even a fraction of an inch, your velocity has entirely shifted. So if velocity is constantly changing like that, how do we actually measure the change? Well, that brings us to section 3, the power of acceleration, measuring change. Okay, so normally we think of acceleration as just mashing the gas pedal to go faster, right? But physics has a much, much broader definition. Because velocity includes both speed and direction, a change in either one of those means you are accelerating. Notice how hitting the brakes to slow down, what we usually call deceleration, is actually just a form of acceleration, just in the opposite direction. And just like we saw with the car on the circular track, turning a steering wheel, that absolutely counts as acceleration too, because your directional state of velocity is being altered. So the absolutely crucial takeaway here is that anytime your speed or your direction shifts over a period of time, you are actively experiencing acceleration. Simply put, it is the rate of change of velocity divided by the time it took for that change to happen. That's it. Now that we've got our core ingredients perfectly defined, we're ready for section 4, kinematic formulas, or as I like to call it, building the physics toolkit. Take a look at these 5 variables. They are literally the alphabet of motion. We've got U for initial velocity, so where you started. We've got V for final velocity, where you ended up. Then A for acceleration, S for displacement or distance, and T for the time it took. Honestly, every single linear motion problem with constant acceleration is just a giant puzzle made out of these exact 5 pieces. And the really beautiful thing is, you don't need to let the math intimidate you at all. Seriously, if you just follow this simple 4-step recipe, you can absolutely crush any linear motion problem. Step 1, always draw a quick diagram to visualize what's happening. Step 2, jot down exactly which of those 5 variables you already know and figure out the one you're trying to find. Step 3, pick the formula that perfectly fits your specific mix of variables. And step 4, just plug in the numbers and solve. It's incredibly logical once you get the hang of it. And here is that toolkit I promised you. By selecting the right equation from these 5 famous kinematic formulas like V equals U plus AT or S equals UT plus 1/2 AT squared, you can completely eliminate the variables you don't know. It allows you to mathematically predict exactly where an object will be, how fast it'll be going, or how long it'll take to get there. It's literally like having a physics crystal ball. All right, let's take all this and apply it to the real world in Section 5, Gravity and Freefall, Nature's Acceleration. Let's see how our toolkit handles a constant force that every single one of us deals with every day, the Earth's gravity. So imagine you're holding something out over a cliff and you drop it. You are initiating what physicists call freefall. At the exact precise moment you let go, its initial velocity, our variable u, is a flat 0. It falls straight down and it gains speed purely because of the Earth's gravitational pull. Now, here on Earth, this gravitational acceleration, which we represent with a lowercase g, is pretty much constant at about 10 meters per second squared. Meaning for every single second that object is falling, its downward speed gets faster by roughly 10 meters per second. And because that initial starting speed was 0, our big, massive kinematic formulas from earlier, they actually shrink down into these beautiful, elegant little shortcuts. If you want to find the velocity of a falling object, you literally just multiply gravity by time, v equals gt. And to find out how far it's fallen, the displacement or height, it's just 1/2 gravity times time squared. It is uniform acceleration at its absolute finest, and it gives us incredibly accurate predictions of any falling object's journey. For our final building block today, let's turn to Section 6, Visualizing Motion with Graphs. We are going to transform all these equations into visual graphs so we can literally see the matrix of motion unfold right in front of us. Okay, so if you plot velocity on the vertical axis and time on the horizontal axis, you instantly unlock a massive visual cheat sheet for motion. When you're looking at a velocity time graph, there are a couple of golden rules you absolutely have to know. First off, the steepness, or the gradient of the line, that tells you the exact acceleration. The steeper the line, the faster the acceleration. And second, if you calculate the geometric area completely underneath that line, it perfectly equals the total distance the object traveled. Seriously, it gives you such a massive shortcut over doing all the manual math. Just look at how this graph puts that exact concept into perspective. See the shaded green area right under this sloped line? Because we already know how to find the area of a basic shape like a rectangle or a trapezium, calculating that shaded space instantly gives you the total distance the object traveled during that specific time frame. There's no complex algebra required at all, just basic elementary geometry revealing these super deep physical truths. But what happens when we start slowing down? Well, a negative slope on our graph simply means the speed is dropping as time goes on. It's a flawless visual representation of deceleration. By just calculating the steepness of this downward slope, we can know exactly how hard the brakes are being applied. So, think about what we've done today. We've gone all the way from defining a basic straight line to untangling speed from velocity, unlocking the true power of acceleration, and finally mastering the formulas and graphs that literally map our physical world. Armed with your brand new kinematic toolkit, you can genuinely predict the future of motion yourself. So imagine a book just got nudged off a 1.4 meter high shelf. You have the constant of gravity, you have the distance. The real question is, using exactly what we've just learned, are you going to try and calculate the exact millisecond it strikes the floor? Dive into the formula, test it out, and see if you can predict the future. Thanks for tuning into this explainer, and remember to keep questioning the physics of the world around you.